Welcome on Electrical Machine 3. I'm Joey Monday and I will be your teacher for the subject. It's an easy subject and it's a bit complex. So what we are going to do, we are going to split our work into small work so that you master each point. By the time you have to combine everything, you understand what's going on. It's a tutorial video, but we're gonna make sure that you understand the concept. We're gonna give you some of the important points, what we feel like you should be. It's really important for you to understand. So on today's video, we're gonna talk about the single phase transformer, and on a single phase transformer, we are going to do an introduction. We are going to talk about the principle of operation of that single transformer. We're going to talk about the EMF equation. We are going to talk about the construction of a single phase transformer. We are going to talk about the equivalent circuit of our three single phase transformer. When it comes to the introduction, this is a transformer. It looks something like this. Okay? And the important point that we should write down is that the transformer is consisting of two electrical circuits linked by a ferromagnetic core. And as you can see, we have a core here. This is our core. Okay? The one that is in gray. That is our core. So you have one electrical circuit, which is just a coil runs across that ferromagnetic. So one side of this electric circuit will be called the primary winding. Okay? And then the second side of this transformer will be called the secondary side or the secondary winding. So it's basically two electrical circuits linked by a common ferromagnetic. But the schematic symbol is something like this, that they say schematic. So you have your primary, you have your secondary, and then you have your ion core. Ion core, it means it's our ferromagnetic core. Okay, that is the symbol we're gonna use. On our second point, we're gonna say that our transformer is a device which used to use the phenomenon of mutual induction to change the value of the alternative current or alternative current voltage. Okay? By the mutual induction, what do we mean with that? So we know that any carrying conductor, if you want it, and then you come with a current, which means you come with an AC source across it. If the current is flowing through this conductor, there will be a flux that will be produced across around that conductor. Okay? So that's what's happening with our transformer. If you come, for instance, on the primary side is where you always put the supplier. So you put your AC supplier on the primary side. What will happen is that the current will flow through our winding. And then if the current is flowing through the winding, what happens? There will be a flux that will be induced. There will be a flux that will be induced in our ferromagnetic. Okay? So this flux will be a mutual flux. It's going to be a mutual flux whereby, because of this flux that we have induced in our magnetic flux, the second side, which is a conductor, and we know any conductor where there is a flux is going to cut that flux. And then once the conductor cut the flux, what will happen? There will be an induced EMF across that. So which means we produce a flux with the primary. The secondary do what? Is going to cut the flux, and because it's cutting the flux, there will be now a induced current across this conductor. Therefore, we're going to measure a specific voltage across the secondary, and then you supply our load. That's basically what's happening with the transformer. Okay? Therefore, the main advantage of AC transmission and distribution, the easy of which a alternative voltage can be increased and decreased. So the device that helps us to increase or decrease the voltage is a transformer. So we're gonna have two types. We're gonna have a step-up transformer and a step-down transformer. And then on the second part, we're gonna talk about the principle of operation of this transformer. And already we have explained already the principle of operation, but let's just explain it in another form. When the secondary is open circuit, as you can see, the secondary here is open circuit, and a alternating voltage V1 is applied to the primary. So this V primary is going to be our V1, the supply. Therefore, there will be a current that will flow in our winding. You see that? And then once the current flow, what happens? There will be an induce. They will produce what? Flux. And then once the flux is produced, what happens? The secondary side is going to do what? It's going to cut the flux to do what? To induce the flux on as well. Can you see that? So that's what happened. Okay? So a small current called no load current will flow, which step up the magnetic flux. In our core, this alternating flux link with both primary and the secondary and induce in them EMF and E1 and E2 respectively by mutual induction. The induced EMF E in a coil of N turn is given by that equation. As you know from electrical one, you have your E, which is the induced EMF. The number of turn of our conductor is going to affect. So we're going to have a change in flux over the change in time because there is a time involved. Okay? And therefore, we can see that the change in time over the change in flux over the change in time is the rate of change of the flux. In the ideal transformer, the rate of change of the flux is the same for both primary and the secondary. What does that mean? It means our E1 over N1 is equal to E2 over N2. Okay? What does that mean? It simply means we say when we are dealing with primary with ideal transformer, our E1 will be equal to E2. Okay? And E2 will be equal to what? En1 will be equal to N2 as well. You see that? Okay? But assuming in our transformer we have no losses, because it's ideal. Okay? So the supplier voltage V1 will be equal to the induced EMF E1. The supplier V2 will be equal to the induced E2. What is the difference between the two voltage? V1 is the supplier voltage from the source. E1 is the induced EMF on the primary side. E2 is your induced EMF on the secondary side. And then V2 will be the supplier voltage from the secondary side, which is going to be the voltage across our load. So because our transformer is ideal, we're going to assume that if you supply 220 volts there, I'm going to induce 220 there. Okay? So if, for instance, my secondary winding, it cuts the flux and induces a voltage of 110, and that 110 will be the voltage across my load as well. So that's what happens when we're dealing with a ideal transformer. Okay? But one thing that we need to write down as well is that V1 over V2 is called the voltage ratio. N1 over N2 is called the turn ratio. But as we're going to be more focused on the transformation ratio of the transformer, which is called a KT ratio. A KT ratio is always going to be given by this. So you should really be used to this, okay? Because we know our V1 is equal over V2, which is the same as N1 is equal to over N2, and then I2 over I1, Okay, so where is this I2 over I1 come from? Because it's an ideal transformer, which means the power in the primary P1 will also be equal to P2. Okay, and therefore the volt P1 is given by what? V1 times I1, and then P2 is given by V2 over I2. So if you apply your cross multiplication, you're gonna have V1 over V2, which is already the voltage ratio, which will be equal to what? I2 over I1. And then this is also a current ratio of the transformer. That's why we incorporate it there. So you should have this formula writing down, because we're going to be using more often. In the case where, let's say they give us the primary voltage, they give us the secondary voltage, and they give us the number of turns of the primary. From this KT ratio, we can be able to determine the number of turns of the secondary. Okay? And therefore, if the number of turns N2 is less than N1, then V2 is going to be less than V1. So this transformer is going to be a step-up transformer. What does that mean? It means that if our number of turns on the secondary is lesser than the number of turns on the primary, which means our voltage that we're going to induce is going to be lesser than the voltage for V1. Already you can see that it's like you are coming with 210 volts across the primary, and then now you step it down, let's say for instance to 100. So already this transformer become what? A step down. And by the number of turns, you can determine that if the N2 is lesser than N1, already this transformer is a step down. If V2 is less than V1, it's a step down transformer. And then if you look at the reverse, what happens now? If the number of turns of the secondary is greater than the number of turns of the primary, this become a step up transformer. If our V2 is greater than V1, this become a step up transformer. And already when you look, you can say for instance, if you come with 110, and then now you're coming out with 220. So this transformer is what? Is the step up transformer. Now let's have a look on problem solving when using our KT ratio. A transformer has 400. Now we can have a look. On the problem solving when using our KT ratio. So you should really master and understand this KT ratio. A transformer has 500 primary turn, and by primary turn we mean our N1, and a secondary turn which is 3000, which is our N2. If the primary voltage is 240 volts, which is going to be our V1, because the primary, determine the secondary voltage, which is going to be our V2. And it says assume this transformer is an ideal transformer. What do we mean by ideal transformer? And once again, when the transformer is ideal, now you can apply your KT ratio to determine the unknown voltage. So you apply your KT ratio, you substitute all the value, and as you can see, the only unknown become our V2. And then in this case, this is our KT ratio function. You substitute all the given value, then you get your V2. So you can see V2 is bigger than V1, so which means this transformer is going to be what? A step up transformer, because you can see that we come with a 240 volt, but on the secondary we have a bigger voltage. So this is a step up transformer. We're going to have a look on another problem, which is going to be our problem 2. An ideal transformer has a turn ratio of 8 to 8 divided by 1, which means we have N1 is going to be 8 turn, and then N2 is going to be 1, or it can be V1 is equal to 8, and then V2 is equal to 1, because they say a transformer has a turn ratio, so it's a turn ratio basically. So we just going to keep on saying it's N1 and N2, and the primary current is 3 amperes, which means our I1 is gonna be 3 ampere. When it's applied, which means our V1 is gonna be 240. Then they ask us to calculate the secondary voltage, which is gonna be V2 and our I2. And again, from our KT ratio, we can determine this problem easily. So how do we do this? You apply your KT ratio, you get the secondary voltage, okay? This is our KT ratio, you apply it, and then you substitute, you get your V2, and then you also apply another KT ratio that involves the current. Now you can get the secondary current. And then you can see that this transformer is a step-down transformer. Why? Because you come with a 240 volts, and now the secondary is 30 volts. Right? So try to walk through it and master this KT ratio, and I'll make sure that I will upload some problem solving or practice question on the KT ratio.